Hello everyone, welcome to the sixth lecture of this series on fundamentals of structural analysis. So in our previous lecture, we have seen a small demonstration of static equilibrium equations. I mean, how we can apply the static equilibrium equations to find out the unknowns, right? So today we will try to understand determinate and indeterminate structures. Okay, so let's get started. So here, what I will do, I will take an example. Suppose we have a cantilever beam, right? So we have provided a fixed support here. It's a cantilever beam, and we have a load on this. Okay, we have a load on this. Suppose W. Okay, W load. So this is my point A. This is my point B, right? And if I see the distance of this W from point A is suppose small a, and from W to B is small b, correct? So now if we draw the free body diagram of this particular system with the load W, so we'll get something like this. I will just draw the beam here. Right now we'll be replacing the support, so we have A and B, and if I replace the support with the forces here, okay, equivalent forces, so we know it is a fixed support, so it is uh, the vertical movement will be constrained, the horizontal movement will be constrained, and the movement will be constrained here, right? Correct. So if I just draw, it will be my AY, this is AX, and here I can say MA. Okay, uh, so this is based on this axis. This is X, this is Y, and uh, uh, we have already I can say considered one you can say sign convention, that the clockwise moment, okay, the horizontal force along this direction and the vertical force along upward vertical force, these are my positive. Okay, these are positive, so this is my sign convention that we are following as of now in the free body diagram. Okay, and then we have this load W, okay, which is at a distance of small a from support A or point A, and B from point B, correct? So now if we apply the equilibrium equations, okay, if we apply the equilibrium equations, we can say the summation of all horizontal forces will be X. So summation of Fx equal to 0. From that we can say Ax equal to 0. So obviously here there is no horizontal force applied, right? So in this case Ax will be 0, right? So again, if we say summation of now the vertical force, so summation of Fy equal to 0. So in this case we can say uh, Ay, which is positive, okay, and then we have a vertical force minus W equal to 0, correct? So from this we can say that Ay equal to W, right? So here we have got one equation, here we have got two equations, right? Now if you see the another one, we have the moment, so we can say summation of moment about A is equal to 0. So here we have MA. Now MA is in positive direction. Okay, now another, you can say, moment which will be induced in this particular point is by this W. Okay, we have this moment MA, and due to this W, it will be W into A, so a moment, and the direction will be same as MA, so it is positive. Okay, so plus, because it is clockwise, so W into A, right? And there is no other force which will be generating moment here, so is equal to 0. Okay, so from there we can say then MA equal to minus WA, right? So what we understood, that the direction of the movement will be basically like this, the value of MA basically, okay, which is the resisting force, or you can say the reaction. So okay, fine, no problem. Now what we will do, we will say this is my third equation, right? So now in all the three equations, what we got the answers. We have three unknowns, AY, AX and MA, and we got this three unknowns resolved, AX, AY and MA, right? So in this particular structure, by using, or the system, by using the equilibrium equations, we got the unknowns, right? We got all the three unknowns by three equations. So there are three equations, three unknowns solved, right? So this kind of structures where the number of equations to solve the, you can say, or to find out the you can say the unknowns, and the number of unknowns are the same, okay, and it is giving us all the results, right? Giving us all the unknowns. So these kind of structures we call as determinate structures. Determinate structures. The structures, okay, where the number of equations, number of static equilibrium equations and the number of unknowns are the same, okay, and we have all the unknowns resolved by the, you can say, number of equations. So those we call this determinate structures, right? Now let us take the same you can say the similar equation, sorry, the similar structure. So what I will do, I will draw the same cantilever beam here, okay, the same cantilever beam, point A, B, right, and with load W at distance A from capital A point and small b from capital B point, right? Now what we will do here, in this B point we will apply a roller support. We will apply a roller support. Now if we draw the free body diagram for this particular, you can say, system, so it will be like this. If you see, this is my A, this is B, correct? Here we have, again I am following the same similar axis that we have followed earlier. So A Y, AX, you don't have to write AX also because there is no horizontal force, still let it be, and MA, correct, MA. Then we have the load W, and then we have one vertical constraint here, which is BY, because it is a roller support, right? So only the vertical direction is constrained, right? So now if we try to solve this with equilibrium equations, so again if we say summation of fx equal to 0, so we know that in this case ax equal to 0, so you just leave it totally, right? Just leave it, right? Because it is already 0 here, there is no horizontal force. Now if we start with the other one, summation of fy equal to 0, from that what we can do, we can say that ay then plus by, then downward w, so minus w equal to 0, correct? Minus w equal to 0. You may consider this as 1, but it is of no use because there is no horizontal force, so it is already 0 always. So from here you can say that ay plus by equal to w, right? So this is one equation we got, so we can say this is my second equation. Now if we take summation of moment about A is equal to 0. So from that what we will get? MA, right? MA plus similarly W into A, right? Let me draw it here. The lever arm is A and this is B, correct? So W into A positive. Now if you see this BY, it is in upward direction and the total lever arm from this A point is A plus B. So it will also generate a this direction moment, right? So it will be negative direction. So minus by into the lever arm is A plus B equal to 0. Okay, equal to 0. We can say this is our third equation. Now if you see here, we are not able to solve our problem, or you can say we are not able to find our you can say unknowns with the three independent equations that we have, right? The three independent equilibrium equations that we have, with that we are not able to find out our, you can say resolve our problem or find out our unknowns, because here ay is unknown, by is unknown, and here again if you see by and ma is unknown. So we have unknown 1, 2, 3, right? And because this is already resolved, so we will not consider this. So in these two cases there are 3 unknowns and 2 equations, right? Only 2 equations and 3 unknowns. So with these 2 equations and 3 unknowns, we are not able to find out these unknowns, any of this, right? So now you may say that in the other case earlier also what we have done, we have taken you can say moment about B to find out the other part, right? So is it helping us in this case? Let us see. So remember, we need an independent equation to find out these you can say unknowns, right? So let us see if it is giving us an independent equation. So if I just take moment about B, so equal to 0, so what there will be? So if you see the first, this ma will add a moment here, so we can say this is giving ma, because this is also induced moment here in the B, plus this ay into A plus B, this whole, it will also generate a moment here in the B, the positive direction, correct? Okay, ma plus ay into A plus B, right? Then minus this W will create a moment W into B in the negative direction. So W into B, right, is equal to 0. Okay. Now from this second equation, if you see, we can replace this ay by second equation. So we can say ay equal to W minus by. So if we use this, ma plus ay is equal to W minus by, right? So W minus by into A plus B minus WB equal to 0. Okay, if we find out MA plus WA minus ABY, okay, plus WB minus ABY, okay, minus WB. Let me just move it a bit. Just move this a bit, yeah. WB equal to 0. Okay, so now if we solve this, what we will get? MA. Now if you see here, this WB will get cancelled, correct? So MA plus WA minus, if I take BY common from these two, I think we have done some mistake. What is the mistake? Minus BBY it will be, right? BBY, sorry. BY if we take common, so A minus B, A minus B or plus B? Minus if we take common, so basically no, it will be A plus B, because it is A, yeah, it is A plus B equal to 0, correct? Right? So if you see, this is the same equation that we have found out here. So this is the basically the third equation that we found out. So these are the same equation. So that means this equation, if we take summation of B equal to summation of moment of B equal to 0, so this is not giving us any independent equation. Ultimately it is giving us back the third equation that we have found out. So from here also we are unable to find any of the unknowns, okay, in these three unknowns. So the structures where the number of equations are less than the number of unknowns, so there we are not able to find out, you can say, the unknowns using the linear you can say static equilibrium equations, right? So these kind of structures we call in indeterminate structure, okay, indeterminate structure. Now there is a term called degree of indeterminacy, okay, degree of indeterminacy. So that means how many additional, you can say, output you require, or I should say output, how many additional unknowns you have compared to your number of equations. Okay, this is the degree of indeterminacy of the structure. That means I will just tell you that here, if you see here, I have number of number of unknowns 3, right? Number of unknowns 3. So to solve this we need 3 number of equations, but we have number of equations, how many? We have 2. So if you say what is the degree of indeterminacy, DOI, so in this it will be number of unknowns 3 minus number of equations 2. So that means there is 1 is the degree of indeterminacy for this particular structure. This is also known as degree of redundancy. Okay, degree of redundancy. This is also known as degree of redundancy. So what does it mean? It actually means that how many number of redundant supports you have. Okay, but now what is this redundant support? That means an additional support. So if you see this you can say beam, this beam we have solved here, and this beam is stable with only this fixed support as well. Okay, this fixed support can make this beam stable under the loading conditions. Okay, but what we have done with this fixed support, we have added an additional, you can say, support here, an additional support here, right? So here, when one number of support which is actually extra, which is not required, without this support also the beam can stand, right? The beam can be stable, right? Or beam may be stable, I should say. So this is what the redundant support is here, right? Here you can see the redundant support. So the number of redundant support is actually equal to the number of, or you can say degree of indeterminacy or degree of redundancy. How many number of redundant or additional support you have in the structure. So suppose just a small example, without solving any equation itself, you can say that what is the degree of indeterminacy of for a particular structure. So suppose this is a what should I draw? I should draw like this. This is a beam and we have a load on this, right? So this is, if you see, there is no additional support for this to take this load. We need these two supports. If I remove this, is it stable? No, it will fall down, right? So we need this roller or pin support here, sorry. Yeah, so we need this roller or another vertical support here. So we got this here, right? Now if I add another roller support here, suppose this is A, this is B, this is B, and now we have added another support. Okay, so basically this support is not required, or this support is not required. If I remove this is stable, okay, and if I remove this, still this is stable. So one of these supports are actually additional, right? So by seeing itself, we can say there is one support additional. So that means the degree of indeterminacy or degree of redundancy is equal to 1, right? So this is what indeterminacy or redundancy is, the additional support that we are providing for a structural system, which actually not required. The structure may be stable without that also, but you have added another support. So the number of such supports the structure having is actually telling or determining its degree of redundancy or degree of indeterminacy, right? So if you go by the theoretical, I can say, definition, it is basically the difference between the number of unknowns, the number of equations. Okay, how many number of unknowns you have, unknown number of equations you have, if you deduct from that, what is the leftover? That will be your number of degree of indeterminacy. But by seeing itself, you can understand that how many number of additional supports I have in this structural system. Okay, so if it is 1, then your DOI is 1. If it is 2, your DOI is 2, right? So by seeing itself, you have to understand. So what we will do to understand this by seeing, we will do few more examples. Okay, a few more examples to understand the degree of indeterminacy, or to understand whether the structure is determinate or indeterminate in our next lecture. I hope this lecture will clear your idea about determinate and indeterminate structures. Okay, and if you have any doubt, you can always write me in the chat, okay, or write me in the comment box. So we'll see you in the next lecture. Thank you.